Hogwarts, Nox, Hogwarts, Lumos. Back in early 2021, I built a Harry Potter-inspired digital assistant for our home. In this video, I'll be sharing the basic technique that I used for the project. From a hardware standpoint, this all runs on a Raspberry Pi and uses a Jabra Speak 510 for the microphone and speaker. Regarding software, I'm using Raspy for the speech recognition and intent detection. I created a framework which I call the conductor that enables developers to handle Raspy intents to perform some action, such as performing a home automation task, getting the weather, or simply telling a joke. While my project focuses on a Harry Potter theme, this same approach can be used to create all sorts of custom digital assistant experiences. Let's get started. The first thing we'll focus on is setting up the conductor. Instead of cloning the repo, I've just downloaded the project as a zip file. One important precondition to be aware of is that the conductor's TTS service relies on Google's text-to-speech API. So you'll need to make sure you have a Google service account set up before proceeding. I'll be using VS Code, but you can of course use your preferred development environment. I already have the project extracted, but before proceeding, let's create a local Git repo to track our changes. Before we set up the Python virtual environment, I'm going to comment out PyGObject from the pip file. While PyGObject will be needed when deploying the conductor on a Raspberry Pi, it's not needed on a Windows platform. With that commented out, I'll create my Python virtual environment directory and kick off the install. While the Python environment is being set up, let's switch to another terminal and stage the Google Service Account file. I already have my file in the parent folder. I just need to copy it into the conductor's config directory. Looks like the Python environment setup is almost finished. There we go. Now we can set up a VS Code launch configuration for the conductor. I already have a launch configuration file set up, so I'll just copy that over to replace what VS Code auto-generated. Okay, we can see the launch configuration is set up to invoke the conductor Python module as the main program, with the address and port being passed in as arguments. Let's fire it up and make sure it's working. The conductor's TTS service can be tested via an HTTP endpoint. I'll be testing it here with Postman and simply sending the text hello to make sure that it is translated into speech.
Hello.
Awesome. This confirms that the conductor is running and able to leverage Google's TTS API. Let's shift gears and take a look at Raspy. It is important to note that Raspy is highly configurable and can be deployed in multiple ways. This video is not meant to be a deep dive into Raspy and will focus only on how I leveraged Raspy for our project. I strongly recommend taking the time to read through their docs to become more familiar with everything Raspy has to offer. It's an awesome toolkit. For this project, I have already installed the Raspy Debian package on my Raspberry Pi. The install instructions in the Raspi docs are very straightforward and didn't give me any trouble. After install, I do recommend setting up a system service to control the startup and shutdown of Raspi. Here's an example of the service configuration that I have set up on the Raspberry Pi to control Raspi. Let's start up the service and review some setup options. It might take a few seconds for Raspi to finish starting up. There we go. If this is the first time starting up Raspi, you'll need to configure each of these settings. Please check the Raspi docs for details on each section. To get a custom wake word of Hogwarts working for our project, I've selected Raspi Raven as the wake word setting, and this allows us to train the wake word to any phrase we wish. In this example, you can see two different training entries, each containing 3 different samples. Hogwarts. The default setting for fisticuffs intent recognition is to enable fuzzy text matching. However, in our house's use case, we seem to get better intent detection with this setting disabled. However, I imagine it will vary depending on your use case, so be sure to check the Raspi docs. We've selected remote HTTP for intent handling. This tells Raspi to transmit the detected intents to the endpoints defined by the remote URL setting. In our case, we're using the conductor to receive intents from Raspi. Normally, the conductor will be running on the same Raspberry Pi as Raspi, which is why the loopback address is being used. However, during development, I want Raspi to transmit intents to the conductor instance running in my development environment, so for now I'll update the IP address to point to my laptop. Next, we'll want to update the sounds used by Raspi. For this example, we're only defining a custom wake word sound, so I'll specify the WAV file to use a chime sound, which will sound like this when the wake word is detected. And we can then clear out the other 2 entries because we won't be using them. Now let's explore how intents are defined in Raspi. This is done in the sentences section, where you'll find an example intent with the name getTemperature. Below its name are the sentences that map to the intent. So if we were to say, what's the temperature? How hot is it? Or how cold is it? Those sentences would trigger the getTemperature intent to be detected. While this example is quite basic, please know that Raspi supports a rich syntax for defining robust intents. Again, see the Raspi docs for more details. We can test intent detection on the Raspi home screen by typing in the sentence we'd like to test and then clicking the Recognize button. As you can see, the getTemperature intent was successfully detected. We'll be using this technique for testing intents during the development process. Okay, let's move on to the fun stuff. Let's define an intent for turning on and off our lights, but with Harry Potter spells. We'll name the intent Change Light State and define Nox for turning off the lights and Lumos for turning them on. You'll see a slightly different syntax used with this intent when compared to the getTemperature example. Our change light state intent defines a slot variable of power and associates a value to that variable based on which sentence was detected. So when Nox is detected, the value for power will be off, and when Lumos is detected, the value will be on. Let's see this detection in action by trying Knox on the home screen. As you can see, change light state was detected and power has a value of off. Note that Raspberry reports the detected intent name and slot information below the Recognize button, so you don't need to inspect the full JSON structure to get those details. Now let's try Lumos. We can see the intent was detected and power value set to on. Now that we have Raspberry configured to detect Knox and Lumos, we need to switch back over to the conductor to define a handler to receive the intent and a service to perform our light state changes. Okay, so I've updated the conductor to define a handler for processing the change light state intent and a service to interact with our smart lights. First, let's review the lights handler. Here you can see a variable is defined to track the name of the intent that will be sent from Raspberry. To notify the conductor that this handler is set up to receive change light state intents, the name of the intent is included in the set of registered intents defined in the handler's constructor. The conductor will automatically call the handle intent method whenever a change light state intent is received. This method maps the received intent to an action method on the handler. In this case, the method maps the change light state intent to the power method on the handler, which in turn calls the power method on the conductor's light service. It's worth noting that while the handler and service method names happen to match in this example, it's not a requirement. If we examine the light service, you'll see this is where the interaction with our smart lights occurs. In this example, we are using LifeX lights and calling their API directly. You can of course develop whatever API interaction makes sense for your use case. If we look at the power method, you can see it constructs a LifeX URL and sends a put request to perform the state change operation. The conductor uses two YAML files for managing configuration. One for application settings that you don't mind being tracked by source control, and another for protected settings, such as API tokens and passwords, which shouldn't be tracked. If we open the application YAML file, you can see an example of how the base LifeX URL is defined. We now need to make the conductor aware of the new lights handler and service that's been defined. This is accomplished by passing the conductor a reference to the new service and handler classes during instantiation. Okay, let's fire up the conductor and make sure it's able to receive the change light state intent. To run this test, we'll jump back over to Raspberry's home screen and test the intent. Since we want Raspberry to transmit the detected intent to the conductor for this test, we need to make sure that the handle option is enabled. We'll try both Knox and Lumos. Okay, both were successfully detected by Raspberry. Let's check the conductor to see if the intents were received. All right, in the conductor terminal output, we can see that both change light state intents were received. The first one with the power defined as off, and the second defined as on. There's one more change to make before deploying our conductor code to the Raspberry Pi. Let's trigger a sound effect during the conductor's handling of the change light state intent. I've already staged a file, lights.mp3, in the conductor's resources directory, and it sounds like this. Let's jump back over to the light service and add a line to play the audio file. All that's needed to play the audio file is to invoke the play method on the conductor's audio service and pass in a play request which contains the path to the audio file. And we just need to adjust our imports to include the play request class. And we're good to go. Next step is to get the conductor running on the Raspberry Pi and test it with our voice. Setting up the conductor on the Raspberry Pi is not too different from running within your development environment. Your project needs to be transferred over and a Python 3 environment configured. To save time, I've already completed those steps. Don't forget, since we'll be running on Linux, we need to adjust the pip file so that PyG object will be included. You can deploy the conductor wherever you'd like on the Raspberry Pi. In my case, I run the conductor in the Pi users home directory under apps. Similar to Raspi, I recommend running the conductor as a system service, and here's an example of the configuration file I use. The conductor exposes an HTTP admin endpoint, which can be used to shut down the service. You'll see I'm simply hitting that endpoint with curl when stopping the service. Let's make sure our service configuration works and start up the conductor. All right, now that the conductor is running, the last thing we need to do is reconfigure Raspi to point to the conductor that is now running on the Raspberry Pi. Okay, we're all set. Let's try this out with our voice. Hogwarts. Knox. Hogwarts. Lumos. Thanks for watching. Links to Raspi and the conductor can be found in the description. I plan to create follow-up videos that focus on additional intent creation, such as getting the weather, telling jokes, and controlling a Chromecast. I expect those will be shorter since I won't have to cover all these setup steps. Until next time, peace.